optimized Genesis sequence.
Good morning. Welcome to the workshop on design patterns revisited in modern Java. My name is Venkat Subramaniam. It's a great pleasure to see you all here today. Let's talk a little bit about what we're going to do here, and then we'll get rolling. We got about 3 hours, but I also am sensitive to taking breaks. So we'll run for about an hour and 20 minutes approximately. We'll take a 20-minute break, and then we'll go for another hour and 20 minutes. During the break, make use of the time to refill your liquids, use the facilities. If you have any questions, I'll be delighted to talk to you during the break as well. So what we're going to talk about today are a few design patterns which I feel are really exciting to use with the evolution of Java. So we'll talk about some do's and we'll talk about some don'ts as well. And then we'll talk a little bit about a few different directions design abilities in Java is moving and how we can benefit from that as well. We'll start, first of all, talking a little bit about design patterns. Now, before we dive into the concept of design patterns, we need to think about when and how to apply design patterns. I've been writing code for a few decades, and design patterns is something that got introduced a long time ago. We have used patterns over time. I would say, in particular, Java programmers have a special fascination for design patterns. I know some of us have probably had it for breakfast this morning before we came here, isn't it? So we love to use design patterns. But there is one problem, I think, with design patterns in general. And to relate to this, let's step back to an analogy for a minute. Now, we all can agree that grandma makes the best pie. You've been talking about grandma's pie for everybody that you know, and you've been saying how you enjoy grandma's pie. Well, your friends tell you one day, if grandma has made such a great pie for you all these years, we're going to come to your house on Saturday. We want you to make that pie. Now, pressure is on. So you call grandma and say, Grandma, I'm in trouble. My friends are coming over. I've been talking about the pie you make. They want to make it. Can you give me the recipe? So grandma says, take some flour, take some sugar. You're like, hold on. I need more help. Tell me how much sugar should I take? And grandma says, oh, take about 2. And you're like, is it teaspoons or tablespoons? You write all that down. And then you tell grandma, can you tell me what are the best practices? What are the do's and don'ts? And then on that fateful Saturday, you wake up early and you make the pie. How did that turn out to be? Yeah, I can hear your laughter, right? So that tells you how it went. Last time I tried something like that, I lost the utensils with the stuff I was making as well. So you meet grandma the next week and say, Grandma, your recipe did not work. It was a disaster. You need to really tell me how to make the pie. And grandma says, why don't we make pie while we talk? And grandma's having a good time talking to you, and she's making the pie. And you notice, how does she add sugar? She takes 2 teaspoons of sugar, measures it very accurately, and puts it right? No, that's right. She's having a good time talking to you. She takes sugar, tosses it in, and does that. You said, whoa, what was that? And she says, sugar. And you ask her, how much did you put? She says, enough. And that's when you realize grandma doesn't follow things like the way we try to do as a novice. Well, what I'm getting to is the grandparents of our industry wrote that fantastic book called Design Patterns about 30 years ago. I know that's a bit scary, right? 30 years seems a really long time ago. I was a very young programmer back then. I'm still a young programmer, but I was a young programmer back then. But I remember reading through the Design Patterns book, and they are the grandparents of our industry. And I think the worst thing the 4 of them ever did in their life is to write that damn book. Because the minute they wrote it, everybody thought, I can read that book and I can do that too. And what a disaster. Well, now that I motivated you so much about design patterns, let's talk about why design patterns are great and why they are disaster at the same time. Design patterns, I feel, is great communication tool. Design patterns, unfortunately, are not great design tools. And the reason I say that is, if you wake up in the morning and the very first thought in your mind is, I wonder what design pattern I can use when I go to work today. I recommend you call the boss and say, you're very sick. Don't go to work. Because systems never get designed by applying patterns that way. You don't just wake up and ask the question, I wonder what pattern can I use today? It's like somebody sitting in a garage and asking, I wonder what tools I can use today. That is not the way you do your work. You are doing something in the garage and you realize, hey, I can use a hammer to drive this in. Oh, maybe a chisel will be useful in this case. Maybe a screwdriver is what I need for this one. So you discover tools to use on the job based on what you're trying to do. You don't plan your day asking, what kind of tool could I use for today's work? That's not generally the way we get things done. Sure, we have a set of tools in our toolbox. You reach into the tools as you need them, but you don't really sit there and ask the question, I got a hammer on my hand, anybody has a need for it? So the point really is, design patterns very rarely, at least in my experience, fit into what pattern can I use? But they are extremely good in terms of a communication tool. You're sitting down, looking at a design, talking to a colleague, and the question is, how does this work? And you can take many words to explain how it works, or you can say, oh, we're using an abstract factory here, or we're using a factory pattern here, or we are using a visitor here. So the point really is, you can use these to communicate what you're trying to do, rather than trying to sit there and devise what you want to really implement. Reminds me of an experience. I had a developer come to me and said, hey, I'm trying to use this pattern in the code, and the more I try, the harder it keeps getting. I'm really getting confused at this point, not exactly sure how to use this design pattern. Can you help me? And I said, I'll be delighted to. Let's sit down. Let's talk about what you're trying to do. And the gentleman starts explaining the problem they are trying to solve. And as we are discussing that, we go to the board, start drawing a little diagram of the design idea that comes into our mind. And a few minutes later, we have a little design to solve the problem that he described. And then I said, what do you think of the solution? He said, gosh, this is really simple. I think I can get this implemented in the next 10 to 15 minutes. Thanks. And he walks out. And then quickly makes a turn and says, wait a second, I came here asking how to use the design pattern, and I don't think we ever talked about that. And instead, we looked at the solution to the problem I have. And I asked him, what is your goal? Is your goal to use a pattern, or is your goal to solve a particular problem? And he chuckled and said, of course, it's to solve the problem. Thanks. This is actually something I can get my work done, and I can move forward. So a lot of times, we get tangled up on using a pattern. My recommendation instead is, don't try to force fit a pattern into your design. Instead, naturally think about design and work towards evolving your design. And let the patterns emerge out of the design. In a way, you can gravitate towards a pattern rather than trying to force fit a pattern, and that is often effective. So having said all of that, the patterns are still useful, like I said, to think about how to communicate a pattern. But of course, there are two kinds of patterns, unfortunately. The good patterns, or the good use of patterns, and of course, the anti-patterns as well, which are things we shouldn't be using, but we often tend to use. So it's important not only to understand how to recognize patterns in what we do, but also to recognize anti-patterns as well, so we don't fall into a trap of using them. So let's start with one particular thing, which is the optional. And I find optional to be useful, but at the same time, it also can be very largely misused. So I want to talk about that to begin with in here. So what is really optional? So let's say for a minute that I want to create a function. Let's say in this case, I'm going to say a string, let's call it as get name, and I want to provide an ID for some name that I'm going to be requesting for from an application. So let's just hypothetically speak about a particular function API in this case. So I'm going to return a string for the get name. But of course, as we can imagine, the ID may or may not exist. So what happens if the ID doesn't exist? So you could say, for example, if ID is equal to 0, just to simulate a fact that it doesn't exist, versus if it were to exist, let's say some name I want to return in this particular case. So I'm going to say some name for a minute. Now the question is, what do we do if the value does not exist? So the problem in this case is a user of the code may be doing something like this. They might be, let's actually make this a bit static so it's easier to use it. So, excuse me, in this case, we could say that we are calling the get name, and of course I'm going to provide a 1, and I could say a 2 uppercase like so, and obviously in this particular case, that's not going to be a problem. We're going to get the some name, convert it to 2 uppercase, and then we're going to simply print it. So that was not an issue. On the other hand, what are we going to do if we don't have the name? So we could be tempted to return a null in this case. Now, I'm going to say, I often repeat this to my developers, that null is a smell. So essentially, they both are 4 letters. So essentially, actually smell is 5 letters, off by 1 error. So essentially, the idea here is that when we use a null, the gentleman who introduced null, Tony Hoare, apologized publicly. He called it this billion-dollar mistake. This is really a terrible idea, but yet we see this quite often in the code. But the question is, what's going to happen if we do have a null being returned? Well, unfortunately, though, one of the things we want to think about from the design point of view is something I'm learning quite often to do, and I constantly think about it. And that virtue, in my opinion, is, code should reveal its intentions. So this is one of the very important design characteristics we want to use. Code should reveal its intention. Now, when you work with things that reveal intention, you get along doing your work. When you deal with things that don't reveal intention, you feel like you feel like an idiot. You feel frustrated. How many times have you seen this around you? Years ago, when my son went to college, I was traveling around the world. He was away from home. But there was one thing that connected us, sadly, I would say, and that is we both in different parts of the world will constantly text each other photos of really bad design we will run into. I would be walking through a hotel, and I would be looking at a door and literally not sure how to use the door. Because do you push the door to open it, or do you pull the door to open it? How many times have you seen that? You go to a door and you're like, do I push it or do I pull it? And you do it in the opposite direction, and then you're not sure about it. The worst thing humans have ever created is the USB. Have you ever inserted a USB correctly? And I'm consistently wrong. And I feel like an idiot every time I use one. So these are examples of terrible design. And we see terrible design everywhere around us. And that should teach us a lesson. How can we design something where it's obvious so people don't have to be cursing us? And that is one thing I think is common, right? One day I work off the basement, and I'm sitting alone writing code. And my wife said to me one day, she said, Venkat, you are the politest person I know. I said, yeah, thank you, thank you. She said, no, but. There's always this but coming through, right, after the statement. But I've come along downstairs when you're working. You don't know this, but I listen to you when you work, and all those filthy words that come out of your mouth. And I told her, well, honey, that's called coding, right? Because we get frustrated when we write code. You're like, what does this code do? And followed by all those, cursy words that we tend to say. The point is, you want to really create a design that reveals its intention. The problem in this code is, what if I were to simply send a non-existent ID? We get a null pointer exception right there. Tell me if you enjoy receiving null pointer exception. How do you feel when you get null pointer exception? If you're not sure about it, I've got a really good friend. You should ask him. And poor gentleman, he had an entirely long day. At the end of the day, he goes to his hotel room and he turns on the TV. And the TV threw a null pointer exception at him. Can you imagine this? Forget about horror movies to watch. That is scary enough. So clearly, an unhandled exception coming off your TV box is the lowest point in anybody's life, I think. So the point really is we don't want to really slip through these things. We want very clear deterministic code. So how do we handle that? Well, one way we can do this in Java is to use optional. Well, certain languages like Kotlin and C#, to name a few, have what are called nullable types. Nullable types are nice that they prevent you from accidentally getting into a null pointer exception. Well, Java doesn't have a nullable type, but what comes close to it is the concept of optional. So I can go back to this code here and say, optional of string in this particular case, and then we can say this obviously is coming from java.util, and I'm returning an optional of string. So back here I can say optional of the value that I want to return, whereas in here we can simply say optional of empty, and we can return that to the caller as well. Now, obviously, in this case, what we want to do is to be able to get the result of it. Let's take a look at that real quick. And we can see that it gave us an optional of empty versus, in this particular case, if we do have a value, it does say optional of some name. So in a sense, we're using a level of indirection. So rather than returning a reference to the caller, we're returning a reference to an object, which in turn holds a reference potentially. Now, the benefit of this, of course, is how do we get the value out of this particular object? So you could say, for example, result is equal to, and you can assign the result in this particular case, and you can have a couple of different options to get the data out of it. Now, clearly, you cannot do the result dot to uppercase, because to uppercase is not a method available on the optional. So that doesn't work, obviously. So what you're going to do in this particular case is to say either an imperative solution. So you can say imperatively, you could say, for example, if result dot is present, you can query it, and if it is present, you can get the value out of it. Otherwise, you can do something about it. So for example, not found, if it were not to be found, you could do that. So in this case, you can see it says not found. But if it were to be available, we can then say, for example, output result dot. Well, there are a couple of options available in this case. One is a method called get. And generally speaking, I'm not a fan of the get method. I recommend not to use get method. So I will simply say, please, I would say, for get. So don't use the method, right? That's not a great method. The reason I say don't use for get is it breaches on, again, that idea of really being revealing intention. Get doesn't tell you that it's going to blow up if the value doesn't exist. Literally, they provided an alternative to get method, which does exactly the same thing, just with a different name, and I recommend using that. So you could say, or else, you could say throw, and that's a way for you to get the value out of it. So or else throw reveals the intention a lot better to say, hey, if it doesn't exist, I'm going to blow up, so you know. So the intention is a lot clearer than using get. So my recommendation is do not use get, instead use or else throw, or or else with a default value, right? So you can say a default that you can provide as well. So those are my preference, use or else throw or use or else with a default value. That is much better. Just to emphasize that right here, you could do that as some name, or you can simply say instead of that, you could have said, or else instead of or else throw, and you can, say, nobody, right? So essentially, you can say whatever you want to say, and you can provide the value for it as an equivalent. So those are some alternatives. So this becomes a nice way. So this is an imperatively you can do so. Or what you can do is more functionally, if you will. You could have said, for example, result dot, if present, and you could write in this case, you have a value, so name, and I want to print the name out. So that's one way you're providing a consumer. Or you can simply say, in this particular case, you could simply say not found to illustrate that the value doesn't exist in this particular case, and you can provide that as well. So that becomes a different way of writing that code. You can say, if present, or else, and you can do something about those two conditions, if you will. So if present, by the way, was introduced in Java 8, but that did not include the else part. But they added a if present or else in Java 9, so you could use the else part as well. So that becomes a little bit more concise code if you want to say what you want to do for each of these parts. Just to illustrate that, we can provide that as well. So that is basically the pattern of how we can use optional. Now, before we go a little further into this, I do have one thing to clarify here. I actually had somebody argue with me about this, and they said, I don't like optional. Well, that's a fair statement. You don't have to like everything, but there's got to be a good reason why not to like something. And I asked them why they don't like optional. And they said, because it doesn't prevent null pointer exception for me. And I was curious. I said, really? Because if you use an optional, you got to really check it before you can use it. And they said, aha, but I write code like this, they said. So they said, return null. Now, you can't, avoid fools, right, from using your language. So this is one of the things to really think about. So clearly, that was not the intention. But the person's argument was, I'm going to return a null where optional is expected. So you cannot make everything foolproof because there's always a bigger fool. And when you see them, just smile at them and say you're awesome and just walk away. It's not worth your time. It's not worth your effort. So clearly, that's not supposed to be done. So don't do that. And if you do have to work with somebody like that, well, there's always another job to look for. So the point really is that optional can be really useful when you return something. Now, let's talk about some anti-patterns we want to consider. One, use optional to return values. Oh, let's actually step back for a minute. So, return a reference if the value will always exist. So this is generally a norm that I would like to use in writing code. Now, I understand we got a lot of legacy code, but as we are writing newer code and as we are evolving code, there are a few practices we can follow. And one of them is return a reference if the value will always exist. So when I see a return type of string or a return type of person, I don't want to question whether that's going to exist or not. I don't want to perform null check. If you perform null check everywhere, that's called being a paranoid when programming. You want to have confidence with the data that you're receiving. So within a circle of your application, you can do this, and you can cleanse the data in the peripheral as it flows through. So my first rule is return a reference if the value will always exist. Return an optional, if the value may or may not exist. So if the value will exist or the value may not exist, then you want to convey that by returning optional. So the minute I see an optional, I realize, aha, this value may or may not exist, so I need to query it before I have to use it. So again, this comes back to the program with intention. You are communicating the intent, so the reader of your code or the API is very aware of what to expect in this particular case. The third thing I would recommend is do not use optional for fields. This actually makes very little sense. So if I'm going to create a field within my class, for example, let's say I'm going to say over here a private, let's say a string, let's say config info of some sort. Well, instead of doing so, should I say optional of really that particular value? So that's a question we want to ask. Should I really provide a string or should I provide an optional? I'm going to say this is overhead with little benefit. So remember, this is your internal code that is encapsulated. You are having a very small area of influence where this can affect your code. That's why we call it encapsulation. When you encapsulate it properly, the sphere of influence of that code is limited. So by protecting yourselves from keeping optional gives you very little benefit. And the overhead of that, though, is that you're not storing a reference now. You're storing a reference to an object that stores a reference. That is an unnecessary overhead you are dealing with. So there's really no benefit to doing it. I would encourage you to rethink about your design. If config information is not provided, I would literally set that to a default. That might actually make sense. So you will always have a value for the config info rather than it being null or empty, because after all, you have to deal with the situation when it doesn't exist. What would you do if it doesn't exist? Well, whatever that is, just store it in there if it's not there, so you don't have to worry about it. So that's one recommendation, is don't use it for a field. And the next recommendation is do not use optional for method parameters. This also makes little sense. Let me explain why in this particular case. Let's say for a minute, I have a public, let's say, a method void, let's say set info, and I have a string info like so. And this is going to provide me some information that I want to set, let's say. Now, obviously, in this case, you are saying, yeah, but the caller of this code will have to do the following. They will have to say set info, and I'm going to say some info they're going to pass in. Or if they don't want to pass in some info, they send a null, and we're not very happy with that. They are sending null. After all, it would be nice to not having to use null, so what's a solution? I'm going to say the bad idea solution is the following. You are going to change this to, in this case, literally optional of string like so info. This, I would say, is really a bad idea. Why is this a bad idea? Why shouldn't we do this? Well, the reason I would argue is, now imagine what we just did. So if somebody wants to pass in information, they have to say optional of and provide the information they want to. And if they don't want to provide an information, they have to say optional of empty. And notice how much more effort it is to call that particular code. Is it pleasant? Is it something? Would you smile when you're writing code? Or will you curse saying, oh gosh, this is stupid. Why am I doing so much effort into calling this function? So the beauty of this is that we can easily use overloading instead. So take a little bit more extra effort, but you're really helping your users of your code a lot more. So what I would instead do, rather than doing this, is I would simply provide two functions like so. I will provide a set info like so, and maybe a static void set info, which doesn't really take any data, or you can even call it as set default info, if that makes it much more clearer. Well, the benefit of that is instead of doing so, you're going to simply say the following. You're going to say set info, some info, when you do have some information to pass in, or you can simply leave it out and not have to really clutter that, and that becomes a lot easier to call it. So it makes little sense to use optional as a parameter because it makes it easier for us. Now, there is exception to that rule. This is when a human is going to call your code. On the other hand, if your code is being called by machine-generated code, we don't care about it. So if you're putting this on a controller in Spring, that's fine. But if you're putting this in a service in Spring, I would have trouble with it. So it depends on where you're putting this code as well. So I would say for most part, avoid this. There could be a slight exceptions, but in general, that's a good rule to follow. So I would recommend that we use optional for return types, but only when a value may or may not exist. Don't use it for fields. Don't use it for method parameters as well. It's a lot easier to fall into a trap and start using features where it may not be the right ways to use it. I've seen developers use this for various purposes. So word of caution, when it could be useful and maybe when we should avoid that is generally a good thing to do. So that is one thing I would recommend is keep your eyes out for it. So you can decide when to use optional and maybe when it's actually an overuse, and maybe you should avoid that as well. So with that said, let's move on to talk about a few other patterns. Design patterns have been around for a long time, but I'm going to say that I see patterns in the light of three different colors, I would say. One is there are certain patterns that have been around for a long time, and we can continue to use those patterns. There are a few patterns that's been around for a while, but I think we would be using them differently thanks to the evolution of the language. And thirdly, I would say there are some patterns we couldn't use before, but we can use now because the language has evolved to provide some new capabilities. But before we go into it, I do want to emphasize one other thing about design patterns. I would say the more design patterns we talk about, the less powerful a language is. So essentially, I would say the more powerful a language is, the more we will use, I would say, integrated features than design patterns. So generally speaking, I remember way back in time, I used to program in C++ for developing commercial applications. And we used to use a lot of patterns. When I started learning Java, I was quite amazed. I was like, wow, all these things we talk about as patterns in C++ are natural features in Java. I don't need to celebrate them as patterns. So I consider Java to be a little bit more powerful than C++, though C++ programmers will get angry when I say that. But they get angry no matter what I say, so that's not a problem. So the point really is that Java really has some powerful features. For example, in Java, we have reflection. So you naturally do things as reflection, whereas when you're programming in language like C++, you got to put extra effort to deal with some of those things that you don't have as a capability. Now, in a similar way, when lambda expressions was introduced, I had a little aha moment because the patterns I would use in Java decided to kind of disappear and blend into the language. I guess that's a name I should use, that they blend into the language. So the more powerful a language is, the patterns blend into the language as a feature rather than standing out as a design pattern. And that is one of the nice things about evolution of language is that more patterns may begin to blend into the language as time goes on, which means it becomes natural for us to use them, and we don't have to put extra effort to use them as well. Let's take a look at some examples of this along the way. Well, one of them is the iterator pattern. Now, iterator pattern is pretty broad, and iterator pattern allows us to really iterate over a collection without having to know the specific type of the collection. So essentially, whether you're iterating over a list or a set, you don't have to worry about the iteration. You can have a common abstraction to iterate. That's basically what an iterator pattern provides for you. But I'm going to take a tangent here and talk about something a little bit different in here. And that is, when I program, I often think about external iterators versus internal iterators. So for example, if I were to say I have names is equal to, let's say, list of, let's say, Tom, comma, Jerry, let's say, and I want to iterate over this particular collection. You could have said for int I equal to 0, I less than names dot size in this particular case. And then is it less than or equal to? That is something you have to think about as well. And I plus plus, and you are wondering, is it I plus plus or plus plus I? All those decisions you have to make. And then, of course, you can pull the elements out of it by calling a get method on it. So that is one way to write the code. And that is essentially what is called an external iterator. And we have used this all quite often in our code for a very long time. Now, of course, this evolved quite a bit in Java 5, but also an external iterator. So you can say for, you can say name coming from names in this case, and you can output more easily the name that you have at hand, so that becomes a lot easier. Nevertheless, that is still an external iterator. But why is it an external iterator? Because in the case of an external iterator, you control every step of the iteration. For example, things, for example, like break, continue, etc., we tend to use them in the code as well. That's basically what an external iteration is. So for example, in this particular case, pardon me, let's say we have a collection of names given to us, and you have, let's say, Darla here, and let's say you have, Bob, and you have, let's say, Jack, and maybe I want to iterate only as long as I don't see Bob. So I could say, for example, if name is equals to, let's say, Bob in this case, I want to simply break out of this loop, and I could say break at that particular point. So in this particular case, as we can see, as we iterate through the collection of names, so we are going to say in this particular case, names dot get of I, obviously in this case, and you can refactor that. We exit when we see Bob. But that's kind of verbose, isn't it? Similarly, you can come back here and say, if name dot equals, in this case, let's say again Bob over here, then I want to break as well. So we are breaking out of that loop in this particular case. So you can ask it to provide that exit out of that at that particular instance. So essentially, the idea behind this is you can pretty much ask it to break out of the loop when it is time. But we can also use an internal iterator. I'm a big fan of using internal iterators because the code becomes a lot more concise, and the code begins to read like the problem statement. It's easier to work with. And this is also comes from the idea of functional programming versus external iterator we typically use in the case of imperative style of programming. Now, again, there's no right and wrong way here. It's just a question of what you are more comfortable with. So if you're using external iterators, you're going to write a bit more verbose code, but I'm a big fan of using internal iterators. So I can say names dot, in this case, for each, and you can simply say system.out and print line, and you can simply print it out right there. So when you run the code, you can see it's printing those names, as we can see right there. Now, obviously, in this case, if you want to really exit out of this, how do you really exit out of that? Well, break is a statement. This is something we need to draw a distinction to. In imperative, you could say, style of programming, we use statements, you could say statements and expressions. This is another aha moment for me. Call me silly, but I get excited about these kinds of stuff. So when you think of a statement versus an expression returns a result back to you. A statement doesn't return anything in general. A statement performs action but doesn't give you any result. A statement will do some work, cause a side effect, cause a mutation, change something in memory, and then walk away. And if you want to know what it did, you got to go look at that memory to know what it did. Well, on the other hand, in functional programming, we often use expressions instead of, you could say, statements. So essentially, that's part of the reason for that is in functional programming, we don't want to cause side effect. You don't want to mutate variables. So as a result, you think about it and say, if I'm programming in a functional style, I'll be doing fewer mutations, doing fewer side effects, which means I'm going to move more towards expressions than statements. Well, as it turns out, break is a statement, so it doesn't play a role in functional programming style. But the question is, how do you break out of a loop? In other words, you want to manage the control flow, but you cannot use a break. So what do you do for that? So in this case, I'm going to simply say that I'm going to start with a stream right there. And then I say dot take while. So take while is the equivalent, if you will. So you could say, in this case, take while is the functional programming equivalent of imperative style break. So essentially, it allows you to break out of a loop or break out of an iteration. So you can say take while name, and you can say name dot equals, in this case, Bob is what we are looking for. And of course, in this case, while name is not equal to Bob is what you are really looking for. So take while name is not equal to Bob, keep continuing. So you can see how, in this case, it walks through. Now, clearly, in this case, the minute it hit Bob, it's exiting. You have to work a little bit through to go through that and process that, and maybe not eliminate it right at that moment. But the point really is that is one option. Essentially, there's an alternative to this as well, which is called a limit, and a limit takes a number rather than a limit taking a predicate. So essentially, in this particular case, if you know how many to process, you can use a limit. This is where you would be iterating, and if you process that many number of elements, you break, or you can do a take while, which allows you to break out of a loop the minute you hit a certain value in this particular case, for example. So you can work through this kind of logic in this iteration, and you can use a functional style versus an imperative style. The beauty of this is, as you're writing code, Java being a hybrid language, you can pick and choose what may make sense depending on where you're writing the code, and you can use imperative where you're more comfortable with it, functional style where you're more comfortable with it as well. So with that said, let's move on to the next pattern here, which is the strategy pattern. I think a lot of us would have used strategy pattern over time, but I want to remind you of what a strategy pattern is. So a strategy pattern simply says, so we have an algorithm of some sort, and we want to vary a small part of it. So essentially, this is where I would typically use a strategy pattern. So I have an algorithm, but I want to be able to vary a small part of the algorithm, keeping the rest of the things literally the same. For example, I'll give an example of where I've used strategy in my experience. I have a large application where we need to perform a lot of computations on various units that I have in my entire application. Imagine for a minute, let's say, you have engineering application where you got devices, and all these devices need to be calibrated based on some computation. Or you can think of an application where I've got a lot of employees and I need to compute a raise for these employees based on certain calculations. So in a sense, you got algorithms to run across an entire application. Back to the engineering application where I have devices, one of the things we had to do was an engineer who is working with the system might want to run through the calculations very quickly, and their real concern is not accuracy at this point, but what they want is convergence. So they want to converge towards a result very quickly rather than taking way too much time to compute. But at some point, as they are working through the application, they may come to a stage where they say, I've got an approximation of what I want, but it's time to get really accurate right now. So they may flip a switch and press compute. Now, we don't want a fast computation, we want a more accurate computation. So I would call that as a strategy, because a user is controlling the strategy, saying, I want fast convergence as a strategy now, versus I want more accuracy as a strategy now, but the rest of the application doesn't care about those details. Knowing those details play a role in the execution of the algorithms. So essentially, that's where you typically use a strategy. Excuse me, but the question is, how did we implement strategy? Now, this is where it's important for us to really step back and not just look at the syntax of language, but the evolution of the fundamentals, and understand not just the shift in syntax, but the shift in paradigms as well. So let's think about this for a minute. Java, if you will, so back in time, Java started out with an object-oriented ideology. So this is, and in general, ideologies can be very problematic because ideologies can blind us into thinking there is one right way to do things. And in the beginning, there were motivations to have that kind of ideology. Because when Java was being created, the popularity was behind languages like C++, which was doing object-oriented programming not so elegantly. So the desire was to show clean object-oriented programming. But at the same time, that can also backfire on us if we don't recognize that that's not necessarily the only way to do it. So back in time, we started with the O ideology. Back in Java, I believe it was 1.1, if I'm not mistaken, we had anonymous inner classes. So if you think about anonymous inner classes, I often define anonymous inner class as a missed opportunity. Because imagine for a minute that back then, rather than introducing anonymous inner classes, they decided to introduce lambda expressions. That would have set us nearly, 14 years or 15 years ahead of the curve. But because we were thinking about object-oriented programming, anonymous inner classes made a lot of sense at that time rather than lambda expressions making sense. But how did we approach strategy back in time? So you would create, right? So you would create an interface for a strategy. That's the very first thing you would have done, is you would have created an interface for a strategy. And then what do? We create oftentimes a bunch of classes or anonymous inner classes, depending on what you're trying to do, to implement, if you will, that interface. So if you want to implement a strategy pattern, you started creating an interface and a bunch of classes. Are we done yet? Oh no, you probably need to create a factory to create those instances as well. And by the time you start implementing strategy, you got a few corporate meetings and you're trying to create interfaces and classes, and you lose sight of why you started doing this along the way. I would call that as a very heavyweight solution. Well, thankfully, we don't have to do that today. But let's step back for a minute. Let's say, what is really a strategy? I want to really ask the question, what is really a strategy? Let me put it this way. It is definitely not a class. So we were imagining this as an interface and a class only because of the ideology that we do everything as classes. Sometimes when we are hung up on the syntax, we can lose sight of the paradigm and the paradigm shift and the paradigm capabilities. I seriously had a developer, I was shocked when I heard this. And the person said, I've been programming in Java for 20 years. I never once had a need to pass a function to a function. I was truly shocked at that statement because we've been passing functions to functions since Java 1.1, masquerading them into objects only because we were not allowed to pass functions directly. So passing functions to functions is something we've been doing for a very long time, maybe without even realizing it. So I would say fundamentally, right? So fundamentally, I would say strategy, a strategy is a function. That's what it really is. A strategy is simply put, it's a function. That is what it really is. You are asking this function, what strategy should I use? And it tells you the strategy you should use, so it doesn't have to be abstracted as a class. So typically a strategy is a function. Well then, what can we do? As it turns out, naturally, we could say strategies, you could say, can be implemented, you could say, in this particular case, implemented using, simply put, lambdas. So this is one of the things where we can benefit from lambdas as a natural way of using the strategy pattern. So let's take a look at an example. I'm going to keep this example really simple, but we can understand where the strategy can be effective in using this. So let's take a look at this real quick. So let's say for a minute that you are working on a problem and you have a function called total values, where the total values is going to take some values. So let's say in this case we can call it as values equal to, let's say, list of a bunch of numbers. Let's go ahead and say here that I want to use, and I want to be able to take these values and I want to be able to total those. These could be whatever the values mean, prices, size of something, whatever that could be, you want to be able to total them. So in this particular case, what I want to do is to simply say values and I want to total. So let's imagine for a minute, you're at work and this is Friday and you got a very interesting party to go to. You've been talking about this for a long time. Your mind is entirely on the evening activity. But you got to get some code done before you go. So you quickly want to finish this and move on. And one of your colleagues says, I really need a function that will total the values of these prices or whatever measures. So you want to get this done quickly. So what are you going to do right away? You're like, fine, you want it really quickly. I'll get this to you quickly. So total values, list of, let's say, values in this case. And what are we going to do? Let's go ahead and start with a very imperative solution. Result is equal to 0. I want to return the result back to the caller at this particular point. So what am I going to do within this? Excuse me. I'm going to say for, let's go ahead and say a value coming from values, and we can say result plus equal to value and return the value back to the caller. Yay, that's done. Can I go home now? Well, your colleague wants you to write one more method, and you're not too thrilled about it because you really want to get going, but they insist on having one more function. You ask them, what is it? And they tell you, I want to be able to total even values. And you're asking your colleague, do you really need both the functions? One to total all the values, one to total all the even values. And they say adamantly, yes, I need both of those. So what do? You don't have patience for this. You really want to go. And so you are just looking at this. There's a bug already there. That's a premonition, right? Knowing what's going to happen. I love it. I love it. There's nature around us that's watching us all the time. Beautiful. So essentially in this case, you're looking at this code and you are thinking, gosh, I got to really go. I don't want to write this stupid code, but I have to write this because my colleague wants it. What do I do? And then you get a immediate inspiration. And you tell yourselves, there's got to be a reason why they invented copy and pasting, right? I mean, think about this for a minute. If you should not use copy paste, why would that be even a feature? In fact, it is so cool that they not only is a feature, they give you this so easily. Control C, Control V. How cool that is, right? So they even have a keyboard shortcut. That's the most useful feature humans have ever created. Don't let anyone tell you copy pasting is bad. They have no clue how valuable that is, right? So you can just Control C that, and you got that in your clipboard, and you do a Control V on it. How cool that is. And now you have a total even values, right? So all you have to do here is to say if the value mod2 is equal to 0, to know that it is even, then you're going to perform the total, not otherwise. So basically, in this case, we have copied and pasted that. We made a small change to that code, and you can see that it's working. So you finish that code, and you're like, here you go. And as the fate may have it, before you say you're done, your colleague says, oh, but wait, I need one more function. I need to total odd values as well. Now you know that copying and pasting code a third time is an act of criminal negligence. But nobody is watching. It's a Friday afternoon. Why not just commit it? You can always refactor on Monday, isn't it? So, excuse me. You write the code, you're on the way, and you're thinking about this, and guilt kicks in. And you know this is not the way you normally write code. You are just succumbing to the pressure of having to release this right away. So you pull up by the nearest coffee store. You want to refactor this because when you go to the party, you don't want to face friends who ask you, how's it going at work? And you're like, oh. And your mind is like, just tell them you copied and pasted. You're like, no, they wouldn't want to hang around with me, right? So guilt kicks in. You want to really refactor the code. Well, let's pretend this never happened. Let's roll back the code, and let's do this the right way to remove all that burden off our shoulders. So here we are. The code is existing, and our colleague says, I need a function to total all the even values. You say, do you need both of those? Yep, I do need both of those. You say, all right, let's go ahead and do a little bit of refactoring before we implement that code. So typically speaking, this is one of the practices I follow often. And that is, generally speaking, I say, refactor before you add a feature or after you add you add, I would say, my fingers are not warmed up yet, you add a feature. So essentially, the idea here is you refactor before you add a feature or after you add a feature, but I would say, but never in the middle of it. So in other words, I typically want to see refactoring as a separate commit in my source code. This is just a discipline. But of course, as you know, this is something I believe in. Programming is 10% skill and 90% discipline. That's what it really is most of the time, I feel, right? So it's all about how disciplined we are in what we do. So when I write code, this is my discipline that needs to kick in and check about what I'm doing. So I'm going to be writing this feature. Oh, but if I really refactor this, it'll make my life a lot easier to write that code. So I'm going to refactor this now, and I'm going to make sure all the tests are passing and commit the code. So once I commit the code, I can then continue to write more code. And this is another principle I follow a lot. So commit often and commit in small, I would say, portions. So why do I want to do this? Because I follow one very important rule, and that is merge hell is what you give and should never receive. So this is one rule I follow, right? So I love giving merge hell to other people. I don't want to ever receive merge hell. So the best is to just keep going, commit frequently, commit in small portion, let them have the merge hell, not you. So the people who don't commit for a long time, they'll come to work and they'll scream because there's a lot of merge hell going on, and you're like, yes, right? So they got what they deserve. No, just kidding, but only partly. So the point really is that essentially in this case, that you want to really keep those commits as often. That's a discipline I try to follow quite often, is to refactor, commit to the repository, and then continue to write more code along the way. So essentially in this case, we're going to do a bit of a refactoring before we add the feature. So going back to this code, so this is one of the things I want to also emphasize about committing frequently. So frequent commits make the cost of undo near zero. So this is the reason I commit frequently. So I want to commit frequently because the cost of undo becomes near zero. When your cost of undo is zero, you're able to innovate much better. If you have not committed the code for a while and you come up with this great idea, oh, look at this, I could change the design this way, like, oh, hold on, you don't want to lose the code you have. Let's be very careful moving forward. So committing frequently makes you go faster. Committing less frequently slows you down in general. These are just lessons we learn, but sometimes when you externalize those thoughts in our mind, it turns into discipline and practices with discipline as well. So anyway, coming back to the program, so what I want to do here is to say, given an element, I want to return true. So we just added additional parameter to the function, argument to the function, which says, given an element, simply return true. So I'm going to go back to this code and say, I want to bring in a dot function, and in this case, I'm going to bring in a predicate. So I'm going to say a predicate right there, which takes an integer, and I'm going to say selector. You can call it as an int predicate if you want to. There's nothing wrong with it. So then I come in here and say, if the selector test of the value were to be true, then go ahead and add it. Otherwise, simply ignore that particular value. So when I run the code, the result is the same, but we just refactored it in this particular case. Of course, this is when I'll be committing this change before I continue to move forward after this refactoring. So now that we modified that, now we can simply say, hey, given this value, I want to simply say emod2 is equal to 0, and we can simply total all the even values as well. Or alternatively, you could also have, in this case, a Boolean is even as a function, which takes a number, if you will. I can say number in this particular case, and number mod 2 is equal to 0. And instead of this, I could have nicely written this as a sample is even, like so, and I could have used a method reference on it as well, rather than having to use a lambda. So we could then, what's happening in this case? I would argue that these functions literally are our strategies, if you will. So you can have a strategy which is even. You could also have a strategy in here which you could call it as is odd, which takes a number again, and it's simply going to return number mod 2 is not equal to 0, as the case would be in this particular case, and you can provide that function here as well is an is-odd function. So as a result, you could simply replace this with an is-odd, and as a result, you can be picking odd numbers to total rather than even numbers, and so that those become a strategy. Now, obviously, you can refactor the original code, which was using imperative style into functional, if you really wanted to. That's perfectly fine. So you could go back here and say, well, maybe I want to really say that I have these values. So we could do a return values.stream.filter, and I'm going to simply send the selector to it. And then, of course, I want to perform a map operation, maybe map to int of the element to element, or you can use other functions in here, and then eventually you can call a sum function on it or a method on it and return the sum of the values, if you will. So you could refactor that as well, if the case may be. And you can massage this a little bit to make it more smoother, but you get the point of how you can provide the functional interface to do so. So I would argue that these become the strategies in this case. Now, clearly in this particular example, we are passing a function in this case, rather than having to worry about implementing anonymous inner classes or implementing interfaces. Now, you may say, oh gosh, but lambdas are really using functional interfaces in the back. Well, that is more of the Javaism in terms of how Java took the pain to provide backward compatibility, but that's not because lambdas require it in general. So that is more of a consequence of Java's route it took. But essentially, what you're doing here is passing functions after all. And as you can see evidently here, it is a function that you're passing using these method references as well. So that becomes your strategy that you can provide. So in a sense, you can say that strategy pattern simply transforms to effectively using lambdas, and you can think of lambdas as strategies as well that can be very powerful. So we saw a little bit of a transition of a pattern from being more heavyweight to something a lot more easier to work with as well. So that is basically the natural transition here into more engaging lambdas for what we do rather than having to create classes. But having said that, certain methods can be useful to provide a certain capabilities. Now remember, Java has default methods. Well, we can use default methods as a pattern to implement the factory method pattern. But let's talk about factory method pattern real quick before we dive into how we can use default methods for it. So typically, what do we do with a factory method? So the word factory and the word method. So I want you to take those words, two words separately in here for a minute. So oftentimes we get confused between abstract factory and factory method. What's the difference? So the factory method, really the word factory simply tells us that an abstraction, you could say abstraction to create an object. That's what it really is, right? A factory is an abstraction to create an object. But what about the word method? What does that mean? This literally means inheritance, hierarchy, if you will, where we can override a method to provide an alternative implementation that we return. So this is why this factory method typically is one that uses inheritance in what you do. So if you're using factory method, typically you have, in this case, typically we have a base class, generally an abstract base class, and derived classes, you could say derived classes, not just one, multiple, that override the you could say factory method, the method that instantiates object. So typically, the way I normally say is this: if I'm using abstract factory, I look to my left or to my right, because a factory is on the side that I'm depending on. That's how an abstract factory works. A factory method is where I look down on the hierarchy. As a base class, I look at my derived classes to provide the alternate implementation. So you can think about it as horizontal dependency in abstract factory, vertical dependency in terms of factory method. That's an easy way to remember the difference between abstract factory and factory method. Now, typically when you're using a factory method, you are using an abstract base class, and you are deriving from the abstract base class to provide implementations. There's nothing wrong with it. But in general, I would say this. In general, interfaces are better than abstract base classes. So again, if you have no other important reason to select an abstract base class, I would typically program with an interface. But the question then is, if I have an interface, I've got a bunch of declarations of methods, but what if I need really a factory method? How can I benefit from that? Well, this is where I would argue that interfaces with default methods are really useful to implement the factory method. So let's take a look at how that could be the case. I'm going to start with an interface, and I'll call this interface as player interface. And the player interface says, I have a default method called play. And the play method is going to say, output, let's say, I like playing. So, and then it has an implementation. It simply says playing with, and it's going to provide play with something. So what is it going to play with? Well, this is an interface, but I want to capture some details with the interface, but allow for me to vary the implementation. How can I possibly do that? So I'm going to say get pet right there. So the player is going to play with the pet. So I say pet get pet is the method, the abstract method that I'm going to provide in there. So it's an interface we created, and the interface contains the default method, and the default method now relies on the factory methods. So though this becomes your factory method on an interface. So interfaces can provide implementation of the default methods, but they don't carry a state, but they allow a derived class to implement that state for you. So that is the benefit you see in this particular case. Excuse me. So how do we provide this? So I have an interface here called pet, but I can then provide a class called dog, which implements the pet interface. And I could also provide a cat, in this case, which implements a pet interface as well, as you can see right there. So now what I can do here is the following. I can say a class, let's say dog lover, is implements, in this case, implements, let's say, a player. So a dog lover implements a player interface, and because the player interface contains a getPet method, we need to provide that in here. So public, let's say, pet, and we can say getPet, and this simply is going to, let's say, return a new dog. And of course, you can color that with more details with names and such, but let's not worry about it. So in this case, I'm going to say we have a method. We'll call it as play or call play. And what does this do? It takes a player as an argument, and all it's going to do is to simply say player.play and invoke the play method that we have up here. So the default method is being exercised. But how do we use this one? I can do a call play new dog lover. And in this case, the dog lover is being sent over to the function, I like playing with dog, and you can see that it's able to call that particular method. Now you can abstract this out to your own applications where you can write a common method up here in the top, which can do the work it wants to do, but the variation of the objects that you want to use can get abstracted in the getPet method. And the getPet method can, or whatever function you're writing, which can return the instances, pardon me, that you want to be able to use. and that becomes a lot easier to abstract it out. Similarly, you can have multiple methods. You can have a method that is going to return something else, and typically that's what you do in a factory method. You have a base class which provides a common operation and allows the derived classes to vary the parts that come together in that particular operation. In this case, pet is one of them, but you could have other things as well. So you can think about an abstract factory, a factory method, and then see how you can use default methods to achieve that. Now, this also takes us to one other thing I want to quickly show you before the break, which is the lambda expressions serving as a lazy evaluation. Now, if you want to execute a certain job, it might take a certain amount of computation, but how do we really defer the execution? So let's take a look at an example of this just to entertain the thought. So I have a compute method, and I want you to think about this compute as a very time-consuming, let's say a slow, operation. So if it is a slow operation, it's going to take some time, and I'm going to return, let's say, times 100, right? So nothing exciting, but imagine this is a slow operation that you want to use. So now, if I want to provide a function like this, so I say public, let's say static. Let's say in this case, we have an operate, and this takes a value, and it's going to do the following, something like this. Let's say if math.random, let's say, is greater than 0.5, it's going to, let's say, use the value, and it's going to use the value given. Otherwise, let's say, for example, in this case, if it doesn't have a reason for it, continue without using the value. So imagine you're writing a piece of code that receives a certain data, but it may or may not use the data. So if this were the case, how would we call this operate function? So you would do something like operate, and you would say compute, and you have a certain value you want to use, and you can pass that value because that value comes out of some computation, let's say. So when you run the code, what's going to happen in this particular case? So in this particular case, obviously, when you call this particular function, what is it going to do? Well, it's going to call the compute, slow operation, and continue without using the value. Notice that was a total waste, isn't it? So when I run the code again, you can see slow operation continue without using the value, and occasionally it uses the value, but it may not use the value also, which is a bummer, isn't it? So the question is, how do you prevent wasteful computations? Well, as it turns out, computer science is an amazing field, but we find weird names for things that really doesn't make sense when we think about it. So in programming, we have two ways to pass data to functions. Now, you may think, aha, I know what you're talking about, call by value and call by reference. No, that's not what I'm talking about. So there are two ways to pass data to functions. One is called what is called an applicative order, and the other is called normal order. What is really rare about this is applicative order is what most of us are used to. Everyone in this room, every single one of us has used applicative order. So what does that mean? The order of evaluation is the order of call or application. So it's like you do what you see, right? What you see is what you get. That's basically what applicative order is. Normal order is rather very abnormal or unusual. That's why they called it normal order, I think, because very few of us, right? So normal order is rather abnormal or very rare. So it's not something we often see. Languages like Haskell do this extensively. So if you're writing code in language like Haskell, you will not really use the value, compute the value until you actually use it. For just a minute, pretend this is Haskell code. Well, guess what's going to happen if this were Haskell? If this were Haskell code, what's going to happen in this particular case is that Haskell will, when you call the function operate, what Haskell will do is it will not call compute. I know that sounds a little unintuitive, right? Haskell will not call compute. So you tell Haskell, hey, I want you to call compute. And Haskell is extremely lazy. And Haskell will look at you and say, you want to call compute? Why? Like, well, why do you want to do that? That's such a boring thing to do. And you say, well, I want to call compute because I want to send the result to operate. Well, then call operate. Why do you worry about compute right now? Okay, I want to call operate. And then it says, but why do you want to call operate? And then you say, because I want to print the result. Okay, now you have a good reason. You want a user to see it. Look at a value-based approach, right? I want the user to see the result. Okay, now let's get some work done. So you literally will call operate, but what you pass to Haskell is not the result of compute, but a little pending request to call compute. And when you get into the operate function, you do some work, and Haskell bypasses the use of value, and it says, ta-da, I never had to call compute, I saved all the effort. That is normal order. A normal order is where value is postponed until it is really needed or never called. If you're super curious about seeing normal order, I'll be more than happy to show you either during the break or during lunch. If you're like, I really want to see Haskell and look at normal order, I'll be more than happy to show that to you. But I won't spend the time during the session for that, but you're most welcome to ask if you're interested in it. Now the question is, we know why we want to do this. You want to save on operations until you no longer can save it. I'm not going to show you the solution right now. I'll show you it after the break. But I want to talk about something before we go into it. These are the things I get super excited about. Call me silly, but this is what gets me excited in the morning. And if you want to ever give an award in computer science, I think that award should go to one person, hands down. Unfortunately, he passed away, but he's a British computer scientist. His name is David Wheeler. And David Wheeler, in my opinion, said the most profound thing that every one of us live every day we write code. So what did David Wheeler say? He said, in computer science, he said, we can solve almost any problem. I think the word almost is he's being humble in my opinion. Almost any problem by using one more level of indirection. So to me, this is the most phenomenal observation that any human has made, in my opinion, because we live on indirection. In every code we write, we have been using indirection. How did we use indirection in C? We use pointers as indirection. And pointers gave us indirection, isn't it? Rather than calling a function, you go through a pointer to call the function. You can vary the pointer. In object-oriented programming, polymorphism gave us indirection. You can just see how deep his thinking was, right? He gave us the indirection as an abstraction. Now we are using indirection in pointers in procedural programming. We use polymorphism, which is an indirection. And that may make you wonder, if procedural programming has pointers as indirection, if object-oriented programming has pointers as polymorphism as indirection, what about functional programming? Shouldn't that have indirection as well? I would say lambdas are indirection in functional programming. As polymorphism, I would say polymorphism in, let's say, OOP, and pointers in procedural. For example, in C and stuff like that. So we see this level of indirection all the time. So my question is, how can we leverage lambdas with level of indirection to provide normal order of execution? So we're going to turn this code, which is using applicative order, and I want to show how we can use normal order instead of applicative order. But we have to follow the order of having break before we do that. So we'll take a 20 minutes break, and then when we come back, we are going to continue with this and explore a few more ideas. So enjoy your break. See you in about 20 minutes. Thank you. Thank you. All right, let's continue. So I want to talk about this lazy evaluation that I alluded to. So we have the applicative order where that's being called before we make the call, as you can see. Slow operation executes irrespective of whether the value is being used or not. So the question is, how could we really make this better in terms of postponing the operation? So I'm going to take that function and show a different way of doing it. So here is the operate, we'll say, normal, let's say, order. So the operate normal order is going to postpone evaluation until the value is actually needed. So that's going to be the normal order. Obviously, just by changing the name, it's not going to do the work. But let's start moving towards that direction. So what are we going to do? First of all, I talked about the level of indirection. And look at the beautiful level of indirection you can introduce. So there you go. The arrow gives you the level of indirection. There you are using the value right away, versus you are using the value with the level of indirection at this particular point. So I want to really take this as a normal order. So how do we do the normal order? You basically push it and say, don't do this right now, right? So you're saying, do that, defer the evaluation of that. So that's basically the normal order, and you can really postpone that. So in order to do this, this is simply a supplier. That's what you are working with. So I'm going to bring in a function, in this case, the supplier. So we'll go to the operator normal order, and we will change this to a supplier of integer, and we will say supplier, right? So the supplier is going to give us the deferred evaluation of that. So what are we going to do then? Well, we say if the value is greater than that, we can then say use the value supplier.get, and that's when we're going to be getting the value at this point. So if we go back and execute this code, you can see slow operation, the value is 2000, but you run the code again, continue without using the value, we never incurred the expense of running it. So it's not really that much effort to do it, but it really gives us the concept of deferred evaluation. So essentially, here's a way to think about it. Think about this like an apple, not the computer, but the fruit. Well, I can give you an apple, and you got a couple of things you can do. Maybe you're really hungry. The minute I give you an apple, you eat it. Well, or you can store the apple away, and you can eat it at the later time, or keep it around, and you're like, I don't really care for the apple, you can throw it away. Or you can pass it to somebody else and say, here you go, I got this apple, maybe you can eat it. So when you pass a lambda to a function, think of it like an apple you pass around. You can run it now, you can run it later, you can save it, you can pass it around, and so on. So that gives you the lazy evaluation ability. So if you don't want to execute something right away, you can simulate normal order by bringing this to execution at a later time rather than running it right away. So that basically is an example of the lazy evaluation. So that takes us to talking about a couple of more things I want to spend the time on. This time I'm going to talk about the decorator pattern. Then we'll talk a little bit about creating a fluent interface, which will naturally blend into a execute around method pattern. Then I'll talk a little bit about sealed classes. And then I'll spend a few minutes talking about OOP versus data-oriented programming and how we can benefit from that as well. So we got a bunch of stuff to talk about as we go through the next part in this presentation. So let's go over to the next one, which is the decorator pattern right here. Now, almost all of us maybe have been introduced to a decorator pattern in the past. I want to remind you of one example. Remember that example from way back in time when we started learning decorator pattern? You had something like, for example, buffered reader, buffered reader, for example, is equal to maybe a new buffered reader, new, maybe in this case, a new data reader, and then maybe new file reader or file input stream, whatever that it was, right? So maybe a buffered input stream. Yeah, that's what it was, I think, right? So buffered, let's say, input stream, and you could say is equal to new, and that's going to be the buffered input stream, data input stream, if I remember correctly. And then you're going to have a file, in this case, a file input stream that would sit here. So a file input stream, and then you would specify whatever details you want to specify. Remember that? How many of us got super excited to use decorator pattern when we saw that example? In fact, you saw that as a decorator pattern, and you looked up the dictionary. What does the word decoration mean? Is it take something and make it scary and ugly, right? So that is not something we get really excited about. But as it turns out, a decorator pattern is very powerful, but it doesn't have to be really scary like that. It can be really effective. So I'm going to give you an example of using a decorator, but just using lambdas. So to understand this, I'm going to give you an example of a decorator. And I apologize to you before I give this example. My mind is corrupt. So almost there's a background thread all the time that is thinking about programming. Doesn't matter where I am. I love the outdoors. As you can see the pictures on my screen, I love the outdoors. But just because I'm outdoors doesn't mean I'm not thinking about programming. Especially, somebody would have a very fancy camera. And when I look at the camera, and this is going to happen to you also, so I apologize. When I look at a camera, all I can think of is decorator pattern. Because they have this camera, and then they have all these lenses, and they would take this fancy camera, they'll remove their lenses, and then they'll put more filters into it so they can take a shot of something in a distance or a different light condition. And every time I look at a camera, I'm like, wow, what a beautiful example of a decorator pattern, right? And if that person is a programmer, then we both are doomed for the rest of the afternoon. Now we talk about coding outdoor rather than enjoying the nature. So the point really here is we can think of a camera as a nice decorator pattern. So here is a class called camera, and the class camera has a function. Let's go ahead and say import, let's say java.awt.color. We'll bring that in. Pardon me. And here I'm going to say a color snap takes a color as an input. And let's start with really small baby steps. It's going to simply return the color given to it, nothing exciting. So I'm going to call a process function new camera and just call it. Let's start with that. So in this case, I'm going to say that I want to start with, let's say, a public. Let's go ahead and say this is going to be a static method, a process, which takes a camera, if you will, and let's say camera. And what it's going to do here is to simply, output camera.snap. Let's go ahead and say in this case, we'll pass to it, let's say a new color, let's say 125, 125, and 125. A good little sample to play with to begin with. So in this example, as you can see, we are passing the color to the snap method, and it just gave us 125, so nothing really exciting. Great. So now I want to go a little further with this, and I want to really make the color brighter. So how do I make the color brighter? Well, here's an idea. I'm going to say, given a color, I want to say color.brighter. So notice I'm passing a lambda to enhance the color. Alternatively, I can also say right here, a color, I can simply send a method reference to brighter, B-R-I-G-H-T-E-R. So I can send the a method reference to it, if you will, rather than having to call a lambda expression. So the question is, how do we really pass that color enhancer as a filter, right? Again, when I use the word filter right now, I'm not talking about filter function and map function in functional programming. It's a filter as in a camera filter, if you will. So to make that work, I'm going to say over here a private, let's say a function takes a color and returns a color. We'll call it as a filter, if you will. So then I say a camera, and the camera takes a function color comma color, but I'm going to take the filters as an argument. Because var arg allows me to send nothing or a variable number of arguments, this works really nicely. So in this case, I'm going to say the filter is equal to, given an input, return that as an output. So this is like a function that's going to take an input and just pass it on, doesn't do anything interesting with it. Then I say for will say a filter coming from filters, if you will. Then I can say the filter is equal to. Now, this is one of the cool things about functional programming. So let's take a quick detour and we'll come back to this. So functions, are composable. So this is one of the nice, interesting things we can do with functional programming as well. So for example, if I were to, ask you the question, what is this? And you can say, oh, that's a pen. Sure, we are really good at it as humans. We abstract things out. And you say, that's a pen. You're absolutely correct. That's a pen. But I can take this apart, if you will, and now I'm going to say, hey, look at this. I got ink on my hand. So in this case, I can pull this out, if you will. I'm not going to go that far. And I can say, hey, look, I can pull this out. And what you're going to see here is a few different things, right? There's a casing that you see here. But inside this, there's a spring, the metal, not the framework. And then you have the tube, which has an ink. And this one has a little thing that you can press on, and I can tear that apart. And if I were to be able to manage this, I would have turned this upon into 10 different things, and I could put it on the table. And now I ask you what this is, and you say, well, you got a metal, you got a casing, you got a rubber material there, you got a metal here. But what are those things? I can put them back together, and then you got a pen. Well, we know what this concept is called. This is called object decomposition. So in other words, objects are made using other objects. Well, great, but if objects can be made using other objects, why can't we make functions using other functions? So here I have a function, and here is another function, but I want to compose those two functions. So I can connect the functions together, and I can create an abstraction of a full function. So I can send that data here, which can flow through this function. The output of a function becomes an input of the next function, and that can flow through. So in other words, we can compose functions just like we compose objects as well, and that can be a very powerful way to do things. So what I'm going to do here is to simply say, hey, given this function, I want to compose it. So filter is equal to filter and then a filter. So in this case, I compose the functions together to form this bigger function, if you will. So this is forming a chain of the function. So in a sense, what we achieved is the following. I got a function f1, I got a function f2, which function f1 is taking an input and providing an output. Similarly, function 2 is taking an input and providing an output. Now I created a function f3. But the way the function f3 works is that it takes an input, and then it passes the input to function f1, takes the output of f1, passes to f2, and then takes the output of that and returns to me. So essentially, that becomes our function f3 in this particular case, which is a composite of function f1 and function f2. So you can create a composite function where the composite function simply is taking the input, calling f1, taking the output and calling the input on f2, and taking the output and returning to us. So that's basically what we did here, is to perform a composite. So we said filter is equal to filter and then a filter. So now that we combine those into this filter, what's the next thing we want to do? So we say a filter dot apply, and we're going to apply that on the input, and we're going to return the result from that particular call. So that's basically what we are doing here, is to bring that together. So let's bring in the function right there for us to use. And when you run this code, what are we expecting it to do? So filter right there. So this is going to be a filter, pardon me. So this is going to be a filter, and this becomes a filter we are using as well in this case. So let's see, cannot find the symbol filter. Filter. Too bad it requires me to type properly. Okay, let's try this one more time. So you can see how the color is enhanced right now in this filtering. But not only that, you can go back to this code and you can now say, rather than brighter, you can say darker as well. And you can see that the color is a bit darker than it was to begin with. But you know where I'm going with this? Because we combine this as a filter, what you can do is you can potentially call this one right here by combining those two as well. So you can say, for example, here is a brighter comma color, and you can then say darker as well. So this becomes your decorators that you can add together. So when you run the code right now, you can see how the color was made brighter and darker at the same time. So what's going on in this particular case? So we can combine a series of policies, you could say policies, filters. You could say, you could call this one as, cleansers. You could have, basically, this is like spring filters, if you will. So data, you can say cleansers. You could also say various other things you can combine together. So for example, you could have a function that is doing handle data, but you can say in this case, a mask function. You can say in this case, function to uncompress, right? So uncompress, you could say unmask and uncompress. And you could then say some other operations, and then eventually you can say, in this case, for example, mask, sensitive data, for example. And then you can say compress. So you can provide a lot of these filters in your how you want to handle the data, and those can become series of handlers that you can provide. So what happened in this case essentially is that your decorators are just functions that you are passing around, and you can combine these things in your code. So if you have a function application where you need to receive a data, and maybe you can validate it, and then you want to transform some data, maybe you want to replace some data with an alternate data, maybe you want to enhance a certain piece of data, you can just start throwing in these as decorators in your code, and that becomes a lot easier. You can leave this code at this point if you want to, or you can say, ooh, I really want to make this functional style. Well, if you want to make this functional style, sure you can. Let's see how we can do this. So I'm going to take this and say, I've got a collection of filters that are coming in here. And I want to take those filters and work with them. So stream of filters gives me a stream of all those filters that are given to us. And then I want to say, bring them down to one single filter that I want to use. So the filter is equal to, and you're going to take a collection of filters and bring them to one filter. Here's a quick question. I got a collection of data, but I want to get one data out of it by somehow combining them. What function would we use for that? Beautiful, right? Reduce, you nailed it. So what does a reduce function do? Notice the initial data you pass in. Given an input, you want to return an input. So that's your first data that you're starting with. Then what are we doing? We're performing an and then operation. So you can say result comma a filter, and you can simply say result and then a filter, and you're going to bring them together to work like so. And so in this case, you're going to bring the stream. So let's bring in the stream in here as well. So essentially, in this case, we are transforming the data using the functional style rather than the imperative style. You can leave it at this if you want to, but something tells me we normally won't, right? Because we want to refactor it even to more concise code. So let's see how we can do that. So I can go back to this code and say, aha, but what is this input arrow input? Well, let's go back to math school. You probably remember we saw this, right? So you have operations like 0 plus x giving you x, and operations like 1 times x returning x. So for those operations like plus and star, those values 0 and 1 are normally called as what function? the bingo, you nailed it. Those are called the identity function. Now you know why that's called function.identity. So identity function simply is exactly that. It takes the input and gives you that as an output. Just like 0 plus x is x and 1 times x is x. Those are identity functions. So function.identity gives you that, as you can see. But of course, you can also use a method reference as well. So you can say function and then, which is what you want to use, and you can remove that other part from here. So that becomes a nice, concise code you can write as well. So that becomes a nice way to refactor that into a functional style. So basically, you take a stream of filters and you reduce on it, and you got that one pipeline that you can use in your code very nicely. So that becomes a nice way to combine operations into that functional decorator that we can make use of. So that becomes your decorator pattern, which is pretty nice. Well, the next two patterns I'm going to show you are fairly related to each other. One is kind of an extension to another, but I want to really show you how we can benefit from writing fluent code with lambdas, and how that can help us to write a very specialized code as well to deal with certain scenarios of resource management. But let's get to that in a few minutes. But let's take an example and play with it. So when we're designing an API, we not only want to make the code fluent, we also want to make sure that it's less error prone. So let's think about a code I'm going to write here. I call it a mailer, if you will. And the mailer is going to have a bunch of functions. So I'm going to say a void, and let's go ahead and call this one as from, which takes an address. So let's take this and return from here. We'll say a from was called, right? So this is just purely to play with the API, so I don't want to get into too much detail within the functions. So similarly, we have a to function, and that's going to tell us to. Then I have a function called subject, and the subject function takes a line, and it's just going to return a subject, right? So it's going to print subject. Then I'm going to have a function called body, and we'll say message, and it's going to simply say that it's a body right there. So nothing really exciting. And finally, I'm going to say send, and the send function going to simply say, let's say sending. So let's say we devise an API like this one. So the mailer has a from, a to, a subject, a body, and a send function. So I want to be able to use this function. So how do I use this? So I'm going to say mailer is equal to new mailer. And then I'm going to say mailer dot from. Well, who is this from? I wonder. So this is going to be from, let's go ahead and say this is going to be from my builder, if you will. So my builder is going to send me an email. Well, who is this email being sent to? Let's say it's sending it to me right there. Okay, so far so good. And then I have a subject. So the subject, unfortunately, is what I get a lot of times from my automated builder. It said, your code sucks. Okay, so thank you for that. And I'm going to take the body. And the beauty of my code is it doesn't suck the way the same twice. So every day it's different. So it's going to send me the details of how it sucks today. So it tells me the code smell details, and then I'm going to send a mailer.send and be able to send that as well in this particular call. So given this, of course, we have the code which is going to do the operation. But when you look at this code, there are a few problems. The first problem is it is very noisy, right? So you look at this, it's like, whoa, look at that mailer. That's really noisy. I'm not too thrilled about the noise level in that code. That's one problem. The second problem in this code is that if you think about this code, you're asking the question, should I, right? So should I reuse the mailer instance or not? Well, there's no clarity to it. If I should reuse it, and if I don't, I'm wasting resources. If I shouldn't reuse it, and I do, I've got an error. But the question is, should that be my concern, right? And I would argue that should be facilitated by the creator of the abstraction rather than me trying to do that. So the question really here is, how do we approach that and be able to make that more smooth? So what I'm going to do for that is to use a pattern which is going to allow us to streamline this operation, and we're going to put those two concerns to rest. So how do we accomplish that? The first thing I'm going to do here is to make the constructor of mailer private. So if you make the constructor of mailer private, what's going to happen? You cannot create an object of the mailer. So notice line number 14 is failing, and that's line 14 where we were trying to create an instance of the mailer. So that doesn't work. So now you ask the question, what gives? How do I use it? So I'm going to say this is a static method now. So public static void send, but the send method now takes a consumer of mailer and we'll call it as a block. So what am I going to do with the mailer at this particular point? So you can see how this send is taking a consumer, a block which is going to take a mailer as an argument. So we will bring in the function.consumer right there. And in this function, we're going to say mailer is equal to new mailer, create a new one, or reuse from a pool, that is the job of the creator, right? Creator of the abstraction. So as a user of the abstraction, I don't need to worry about it. Right there on that line, I can create a pool, and any mailer that's not being used, I can pull it from the pool and I can use it if I wanted to, right? I can do that. Then I can say a block.accept, and I can pass the mailer to it. And so the mailer can do the initialization work it wants to do, and then I'm going to say sending and finish the operation in the end. So how is this going to help? So we can go back to this and say mailer.send. So notice now we have a send method we are calling right there. But then I'm going to come down all the way to the end and finish up that particular call right there as a parameter. I'm going to say mailer arrow, and then I'm going to make one small change before we move forward. I'm going to go back to this and say this becomes a from, and it returns a mailer, and that returns a mailer, and so do those two things. And then I'm going to say return this. So I'm going to say return this as a response at the very end of those functions. So as a result, I can go back to this code and say mailer, and I'm going to simply call that on the mailer right there. But guess what? I can simply start chaining them. So I can remove all those semicolons, and I can simply remove those calls as well and start really combining them into one particular sequence of calls. So send says, once I give you a mailer, you can call the from to subject and body on the mailer. So as a result, when I run the code, the output is exactly as it was before. However, there are two things we did. Well, first of all, the code is less noisy. And secondly, if mailer, right, if mailer instance should be, you can ask the question, right, reused or not is not my concern. So I don't have to worry about it. The creator of the abstraction can take care of that. If they feel like it should be reused, let them reuse it. If they want to create a new instance, let them create a new instance. I don't have to worry about it. So this gives us a fluent interface. So we did a couple of things. We returned the current instance from these calls, and then we also received a consumer from this. And as a result, the consumer is able to chain these operations together, and then as a result, we don't have that repetitive calls to that, and we're able to nicely chain this. So this looks almost like a builder pattern that you can use, but this is more general than builder in terms of the fluency that it provides to us as well. So with that said, we're going to take on this idea, but we're going to work on something very similar to this in the next one. So in the next one, I'm going to use a pattern called the execute around method pattern. This is one of the interesting things that we can learn and we can discover. So other languages have had this capability for a while because other languages have had lambdas for a while also. And I came across this pattern in a very old book by Ken Beck called I think it's called the Small Talk Best Practices. That's a book I think I read a long time ago. And when I was reading the Small Talk Best Practices, I came across this pattern that truly inspired me to think about how to make use of that in languages like Java. So let's take a look at the problem first and then talk about the solution. So this is the problem I ran into for a client. So they called me up and they said they got an application in production and the application fails, and they don't know why the application is failing. Now, imagine you are being called as a consultant. They tell you, come fix a problem, and we don't know why the problem exists, but you got to help us to fix it. So I went in as the boss, and I said, hey, can you tell me about this problem you're having? And the boss gave an answer you would expect from bosses, and he said, go talk to my programmers for the details. I just want you to help us to fix the problem. I'm like, all right. So I went to the programmers. What puzzled me was no programmer would give me a straight answer. I asked them, hey, I was told there's a problem in production. Can you tell me what the problem is? And most of them said, I don't know what the problem is. We have some problem. I cannot tell you what it is. So I'm like looking for somebody to help me. And finally, I found Joe. Joe nailed the problem. And Joe said, the code works fine most of the time. I said, yes, that's awesome. And then I said, can we distill down to when it doesn't work? He said, oh, that's easy. It doesn't work between 7:15 and 9 in the morning. And I said, wow, that clear, 7:15 to 9 in the morning. He said, yep. And I said, every day? He said, no, only Monday through Friday. It works fine on Saturday and Sunday. I'm like, wow, why would a code work on the weekends but not work on the weekdays and only between 7:15 and 9? So I said, that's very helpful, thank you, and I will get back to you with more questions. And I started doing code reviews for their project. One of the things they hired me for was also to help them with the code quality. And I stumbled upon a piece of code, and literally, this is an example of what the code was doing. So there was a class, let's call that class as resource, if you will, for lack of better words. And in the resource, they had a constructor, and in the constructor, let's go ahead and say OpenDB connection. So that's what they were actually doing. In the constructor, they were opening a connection to a database. Then they had, of course, operations, right? So you have an operation, we'll call it resource op1, and this one was simply doing some operation, we'll call it op1, and it was returning, in this case, the current object. So similarly, they also had another function, we'll call it operation2, which was doing some work. Now you know where this is going. And then I stumbled upon the next line of code that shocked me. They had a function, public void, finalize, and in the finalize, they had a beautiful call that did the following, close DB connection. And I looked at this code, and I'm like, wow, really? The problem is that in this particular case, they were, so what was the reason why this could be creating a problem? Let's call a function new, if you will, where the use function, let's go ahead and call this one as use, and the use function does the following. Resource is equal to new resource dot, let's say, op1, and I call resource dot op2. So I call the two operations like so. Now here's the problem. Their application had a lot of memory most of the time. And when you create objects after objects after object, well, if you have a lot of memory, the garbage collector doesn't have a reason to run. And when the garbage collector doesn't run, what's going to happen? the finalize method is never executed. When the finalize is not executed, the closing the database doesn't happen. And as a result, they were getting connection errors in the database that went unnoticed. Now, why did it have problems only between 7:15 and 9 in the morning? That's another sad news. This code was running within a portal. And it doesn't matter whether anybody cares about it or not. When they come to work between 7:15 and 9 in the morning, they're logging into the portal, and it was executing this particular code, which means that during the day, not many people were using the application. But in the morning, it was being executed when people log in. So that was the reason for it. So when you run this code right now, notice that it says OpenDB connection, but it never released it. So that's a problem. What should we do to fix it? Well, the first thing is to know that the finalize should have another name. It is called a bad idea. So this should not have been done in the first place. Why is finalize a bad idea? This, again, I want to emphasize, goes back to some very fundamental design ideas. This is what I love about our field. You can look at a problem, you can walk away, or you can stare at a problem and you get a deeper understanding and a deeper realization. So this is my understanding and realization looking at this. So one of the things that we should never do, right? A common design, I could say design flaw or anti-pattern, you can call it as, well, Rich Hickey, the gentleman who created Clojure, created a new name for this. He calls it complecting. And that's not an English word, but complecting is a new word he created. I like to call it as intertwining. So essentially, you are creating two separate things that shouldn't be combined together, but you're putting them together. This is a very common design flaw we all always do. We bring two things that shouldn't belong together because it was convenient. Now, if you really think about it, this finalize is an example of complecting or intertwining. Why is this a bad idea? Well, remember, you have this idea of garbage collection, which takes care of memory at runtime. But we're not dealing with memory right now. Finalize is about external resources. Combining memory management with external resources is intertwining. And anytime you intertwine, it's a question of when it's going to backfire on you. So this is why they very cleverly, finalize has been deprecated starting Java 9. So starting Java 9, if you use finalize, you will get a warning. You say, dude, why didn't you get a warning? I just didn't show you the warning. That's why. But if I were to really run this in code, it would show the warning. I just kind of hid the warning from you right now. So finalize is a bad idea. We shouldn't use it. So what's the solution? What should we do? Now, an answer to that question is a feature they introduced in Java 9. Okay, Java 9 deprecated, right? Deprecated finalize. But before this, preparing for this, in Java 7, they added a feature called ARM, which stands for Automatic Resource Management. So automatic resource management, some of us may know this as, also known as try with resources. So I'm not a fan of try with resources. I'll tell you why with this example. So automatic resource management or try with resources. So what can we do to avoid this problem? You could have said implements auto-closable, and you can then simply change this to a close method. So now auto-closable, and you have a close method given to you right here. And what you can do then is to simply say try like so. And in this particular example, you are bundling that into the operation right there. And you can say resource op1, resource op2. And you can put the block in here to say you are done with that particular resource. The beauty of this is close is called automatically for you here. So even if there was an exception, it will still call that method. That's one of the benefits you have about this particular approach. So if you run the code right now, what you notice is the close DB connection happens automatically. So you say, okay, that works, right? So why are you complaining about it? You could ask. Well, the first thing I want to emphasize here is, well, this is great so far, but what if you don't call the try? So what if you forgot, seriously forgot, to call the try? So the question then is, if you don't put a try, will the compiler give you an error? What do you think? No, it doesn't. Will the compiler giving you a warning? No. So is there a guarantee that you handle it? Not really. But you know this already, right? Because from the beginning, there was a clue that was there. Maybe you missed it. And that is, never trust a feature with the word management in its name. So we know this already, right? So the point really is that this is not going to give you a safeguard. It just tells you if you follow these rules, you will be able to benefit from that. This is why I'm not a fan of try with resources. I want to remove this burden from the hands of a programmer. I want the programmer to sit back and say, I don't need to worry about it because you're going to take care of it. So how do we really deal with it? So let's go back here and get rid of the auto closable. Thank you, no thanks. What I'm going to do instead is, I'm going to go back to this code and say, hey, let's make this close. Well, let's come back to that in a second. I'm going to go back to this and say, hey, resource.close, which is a terrible idea. We don't want programmers to do this. Why? Because if they do it, if there was an exception, this will never be called. That's a disaster. Then they start putting try and finally. That's going to become verbose code. No, thank you. But what I'm going to do is, I'm going to make the close method private. So by making the close method private, you cannot call close, as you can see right there. So now that you cannot call close, all right, fine, I don't call close. That didn't solve the problem for us. Now I'm going to make the constructor itself private as well. So I made the constructor private. So now I cannot even create an object of resource. So line 22 fails. So what gives? So here's what I'm going to do. I'm going to go back to this code and say resource.use, just like we did in the past example. Then I get a resource as an argument. Then I say simply resource.op1 and then .op2, and I'm going to call those methods in sequence. Just like the Fluent interface example we saw, we're going to simply call those methods like so. So what is the use method? So I'm going to say a public, let's say static, let's say void use, takes a consumer of resource, we'll call it as a block like so. So I'm going to bring in a consumer, so that's a function dot star. So we brought in a consumer. What are we going to do now? Then I say try with a finally block, as you would imagine. Then I say resource is equal to new resource, and we will come back here and say resource.close on the finally block. Then within this, I'm going to say the block.accept, and we will pass the resource over to it. So when you run the code this time, you can see the close operations happens automatically. So I've used this pattern quite a bit in my code, and this is extremely powerful in terms of capturing the essence of the things you want to do. I'll give you some examples of this. So in Scala, they call this the loan pattern. They call it a loan pattern because this is as if you get an object on loan. For example, I go rent a car. Before I get the car, I hope they cleaned the car really nicely. And when I return the car, they check for damages. So that's the loan pattern. There's a pre-op and a post-op. There's a before operation and an after operation. So essentially, in this case, you can see that we are calling the use, and we are given a resource. Before you come into this code, the resource has been created. You can do any pre-ops in this case. And when you leave the block of code, what is it going to do? It's going to do the post-op. I'll tell you where I used this. I was working on an application where we had several controllers where we got to perform operations within a transaction. And what I noticed developers do is they copy and paste code to start the transaction. Then in the middle is their code, like a sandwich. And then there's code to do post operations. And I noticed anytime they start a new controller, they would copy and paste code. Somebody told me that's called template-driven development, not the type of development you want to do, right? So quickly we realized there was so much duplication in code. Ooh, how do we avoid it? So here's what we did. We wrote ourselves a class called transaction, and within the class transaction, we wrote a function called run in transaction, and we provided a consumer of actually a runnable, or actually a consumer of transaction object that we created a block. And guess what we did? Within this code, right? So let's say within this code, what we did was we would start a transaction and then block.accept, right? Block.accept, and we provided a transaction to it. And then when you come back from it, if OK, commit, else log and roll back. So we wrote a message like that, method like that in our transaction. How did we use it in our code? We simply said transaction dot run in transaction, and we got a transaction object on our hand, and we went about doing our work. And when we finished it, it was able to check a condition and decide what happened based on that particular condition within the transaction object. So essentially, you can start capturing these kinds of policies in your code, and this can be a very, very effective method. I've seen this pattern used extensively in other languages, like performing file I/O operations. You open a file, but you don't have to remember to close it. When you leave the block of code, the close happens automatically. That can be very powerful as well. So that is basically the execute around method pattern. Like I said, some languages like Scala call it as lone pattern. If you ask me, this is one of my most favorite patterns. I like it for its elegance. I've also used it quite extensively in my own application development as well. So this is one of my favorite patterns for that reason. Having said that, I want to talk about two things left here. One is about sealed interfaces and sealed classes. Excuse me. And the other one is about a little bit about data-oriented programming. I'll keep the sealed minimum so we can spend a little bit more time on data-oriented programming in here. So let's talk about sealed really quickly. So let's say for a minute, I'll give you an example of a use case where this can be really helpful. There are times when you could be creating a piece of code with a certain number of classes and interfaces. Imagine this for a minute. Imagine you are a creator of an open source library, and you put this out there and say, folks, this is a service this library provides. Go for it, use it. And now people are beginning to use your library. And let's say your library has two kinds of interfaces, let's say. So what are the two kinds of interfaces? One, for others to implement, and two, for others only to use. So in other words, when I create my library, I want you to implement some interfaces. That's awesome. When you pass an object to me, I can look at your object. It implements my interface. That's great. My methods can receive it. I can use it. But I've got a few interfaces that you can use, you can call upon services on those interfaces. But I don't want you to ever implement those interfaces. Now, think about this for a minute. Look at the string class. String class is very powerful, but nobody can implement string because it's final. So final classes are awesome. If you make a class final, you're telling others you can use this, but you are not allowed to extend it or implement it. Unfortunately, interfaces are for extensibility. So if you create an interface, anyone can implement. But now you're saying, no, no, dude, don't implement my interface. I got a bunch of classes that implement the interface. I marked all the classes final. Your job is to use any of the classes, but I dare you not to implement the interface. Well, how do you enforce that? Well, I've got clients with similar problems. Here are a few solutions I've seen people use. One solution, during runtime, you can take an object, look at the class of the object. If it's not one of yours, you could scream and fail. Good job. You're going to make enemies out of people using your library. They're going to say, duh, if you told me I shouldn't do this, I would have saved time not implementing it. And after all this effort, I get a runtime error. And you're not going to be happy with that. Well, here's a second solution I've seen people do. The second solution, you can implement your own annotation processor. And you can annotate your classes and make that annotation package friendly. Now, if somebody were to implement your interface, your annotation processor will wake up and say, hey, do you have that interface? No, you don't. I'm going to fail the build. Well, good news. You got a compilation error. So people are going to be less unhappy because they get a compilation error saying, you're not allowed to implement this interface. Ooh, so I should use it, not implement it. Great. But you need to put a lot of effort to create that annotation processor code and then to maintain it. So what can we do to avoid that problem? Well, this is where, as an example, a sealed can be very helpful. So to give an example of this, I'm going to create a traffic light, and I'm going to say traffic light is equal to new red light for a traffic light. I'm going to output the traffic light as well. So very, very simple code. Let's go back here and create a traffic light.java, and I create an interface called traffic light, and I've also created a final class called red light, which implements the traffic light. And likewise, I also have a yellow light and I have a green light as well. So these are three classes that implement that interface. Now, this is going to provide us the implementation for the three, and I run the code, you can see the traffic light. But I want to limit who can have these classes extending from the class. So I'm going to go back to the traffic light, and I say sealed interface traffic light. So now I have limited the children of the traffic light to be only these three by default. Or you can say in here, in this case, you can say permits, and you can say red light, yellow light, and also green light, and you can add to the list if you want to. So this says those are the only three that are permitted to implement that particular interface. So far, so good. If I go back to this code, no problem. However, if I said final class broken light, so I create a broken light implements the traffic light, you notice that gives us an error. The error says class is not allowed to extend sealed class traffic light, even though it's an interface, as it is not listed in the permits class. So you cannot implement from traffic light. Why not? Because you don't belong to the list of classes that are allowed to implement that interface. However, if you really want to implement what's called, let's say, a flashing light, you can ask for permission to implement. So you can go back to the traffic light, and here you can say, comma, flashing light. So now that you added a flashing light, so what does that give us? So you can see in this particular case of this particular code, when I run the code, we don't have an error. Why? Because flashing light is a member of the hierarchy. However, if you were to take a another one, let's call this as broken light. So in this case, that's not a member, and you got an error that you cannot implement it. So as you can see, this provides you a set of classes that you can implement. So the question is, where can these implementation classes be? There's two answers to that question. So the first answer is as follows. So the first answer is, if you are using modules, then the classes, the child classes, right? Child of sealed may be in any package, but within the same module. If you are not using modules, you should. So if you're not using modules, then the child of sealed has to be in the same package. So essentially, that's a rule that you have to know. So if you're using modules, then the child of sealed may be in any package, but within the same module. If you're not using modules, then the child of sealed has to be in the same package. It could be in a different file, but it's got to be in the same package. So that is a rule you have to follow. So that is about sealed to give you that benefit. But I want to take that discussion further into an area where we can benefit from rethinking about how we write some code. And this is where I think we need to be a bit careful. So the first thing is paradigms are there to help us and not the other way around, right? So you don't have to use a paradigm. The goal is to solve a problem. And you want to use a technique, an approach, a way that makes sense for what you do. And if we become adamant and say there's only one way to do things, we are at the loss in general. So I often think about these techniques as tools. I don't want to be attached to a tool. I want to use a tool that makes sense for a problem at hand. If a hammer is the right tool, that's great. If a scissor is a better tool, that's fine. I want to use a different tool for the problem at hand. And don't get me wrong, there are some very powerful tools, but that doesn't mean that's the only tool we would use or only approach we would use. So OOP is awesome. It helps us to develop extensible code. So I'm not going to argue with that at all. Object-oriented programming is absolutely awesome. It helps us to develop extensible code. But we are now hearing about what is called data-oriented programming. What is data-oriented programming? But wait, why should I use it when I have this beautiful object-oriented programming with me? So here is a way to think about it. Object-oriented programming is awesome. It can help us to develop extensible code, but there are times when using OOP may lead to bloated code with many levels of, you could say, hierarchy that makes the code, you could say, cumbersome and hard to maintain. So this is where you may want to really rethink about it. OOP is great, but I don't want to force myself into using it when I'm going to be creating way too much code than I really need to. So let's think about an example of this and why you may want to think about moving away from just using OOP. You're not using instead of OOP. You're combining OOP with something else because that gives you a better tool, a better idea. So let's think of this. So suppose you are creating a hierarchy of classes. So you're creating a hierarchy of classes. So like what? For example, you have a vehicle, a car, a truck, is the hierarchy you're creating. So when you create this hierarchy, what is the benefit? Your vehicle can have an abstract method, right? So it can have an abstract method, which is nice to have, and your car and truck can override that method. So what are we doing here? Polymorphism, right, at work. So that is the beauty of this code. So you have a vehicle interface or a vehicle abstract class, and you're saying, I got a car, I've got a truck, but I can use a vehicle and I can simply call the method. For example, a vehicle, you could say dot drive, where depending on a vehicle at runtime, it may refer to a car or a truck, and the appropriate, you can say appropriate drive is called for us. So the code is very extensible. That's beautiful, isn't it? And here's the bonus, right? If we add another a type of vehicle, say a boat, we can rely on polymorphism, so to make the code, the calling code, right, extensible. That's the beauty of it, without having to change. We celebrate this as open-closed principle. So we're not disputing any of that. All of that is awesome. We can use it. But at some point, you have to ask the question, is this helping me or making things worse for me? So let's take a different example right now. Suppose you are using a library with a hierarchy of classes. So suppose you're using a third-party library with a hierarchy of classes. So they provided that hierarchy of classes for you. And what do you have to do? You have to implement logic that is different for different classes in that hierarchy. So essentially, if you think about it, you are getting a third-party library. This third-party library may be external or could be internal to your company. You just don't have access to change that library. That happens too, right? So you have an access to a library you can use, but you don't have ability to change the source code for it. So suppose you're using a third-party library and a hierarchy of classes are given to you, but you have to implement logic for different classes in different ways in that hierarchy. What is the OOP solution for this? So how would we implement this in OOP? Any ideas? What was that? Instance of will violate extensibility, right? Wishful thinking, please. Visitor pattern. Raise your hand if you have used visitor pattern and you are happy at the end of the day. Not a single hand went up. One person is flashing the camera at me. Are you asking for support? Rescue me. I like your answer. You nailed it. But it makes the point, isn't it? It's a lot of code for you to write. And after you write all that code, your head is spinning. And you're trying to explain this code to somebody. And you're saying, isn't that awesome? And they're like, not exactly the word I would use. It was a lot of work, isn't it? So you could use visitor pattern. So could use visitor pattern, create a parallel hierarchy of classes. So what you end up in this case is the following, right? So suppose you had a vehicle sitting up there, and within that you have a car and a truck. And what do we normally do? You have a vehicle processor. You may create a hierarchy, and in this case, you may create a car processor and a truck processor. Now, the problem with this approach is the minute you see the hierarchy changing, right? So the minute you see the hierarchy changing, you have a boat being introduced here. You got to create a boat processor. You have a sports car. You got to create a sports car processor. So you create this parallel hierarchy of classes, and that can become really messy. So what's the problem? There are two problems with this approach, right? One, a lot of code to write. Two, bloated. It's got too much things going on. And then hard to understand where all the logic is being done. Imagine explaining to a business person about the handling of the logic. You need to be sifting between files to show, oh, look, this is happening here. Let me show you there. Let me show you there. And they're like, excuse me, what was the other file that you showed me? And little code. Oh, that's another thing, right? So little code, little code spread out in so many places. So again, I'm not suggesting OOP is bad. I'm not suggesting don't use OOP. I'm just suggesting that there's a tipping point beyond which it can become burdensome. So this is where we could think of data-oriented programming. So what does data-oriented programming say? Data-oriented programming says, let's think of this as data. Let's take a procedural approach to deal with logic related to multiple types of data. This works, I would say, works really well when dealing with, I would argue, a third-party hierarchy of data. So when you're dealing with a third-party hierarchy of data, but you need to do different things based on the type of data, this can be really powerful. So let's take a look at an example of what we can do with this and how it can benefit for us. Let's say we go to this example of vehicles we talked about. So imagine interface vehicle. And I want you to think about, so imagine these are from a third-party library, right? So we have vehicle, and we have a class called car, which implements vehicle, and we have a class called truck, which implements vehicle as well. So now imagine the following is our code, right? So that's a third-party code, but here we are in our code. So what do we want to do with our code in here? So you might say, process, right, whatever that is, new car, or you want to process a new truck. So you may bring in a truck for processing in here. So we have a truck. But you want to be able to process these objects. How do you handle that? How do you process it? So you can say here, public static, let's say process. Actually, let's go ahead and say string process. And I want to simply return the output of this code. So we'll say output, right? So we'll output the result of that. Similarly, we will simply say, here is a truck I want to output as well. So what am I going to do with the process? The process takes a vehicle as an argument. So we say vehicle. And what are we going to do within this code? So going back to your comment about, let's use instance of, right? But instance of makes the code non-extensible. This is where you deal with the trade-off. And you say, yeah, it's going to make the code non-extensible, but in reality, it's not going to change that often, right? This is where trade-offs are important. We can take a certain recommendation and run with it and be adamant about it, or realize in reality, the number of times it affects us is not that much. And so maybe it's not a bad idea. Maybe we can clean it up a little bit so it doesn't appear that strange. So he nailed it when he said, use instance of, right? Because it's a trade-off. Here is where we got to think of trade-offs. I'm dating myself, but about 40 years ago, when I had to write code, the tools available for me were very different from tools that people had available today. There were no IDEs back then. I know. Some of the young programmers are like, looking at me is like, really? You had no IDEs? Nope, there were no IDE. I mean, hearing that he wants to leave the room, right? He just couldn't take it. So there were no IDEs, literally back in time. And often people look at me and say, so you had no IDEs to work with? Like, nope. And then they ask me, so what do you do with dinosaurs that came around when you're coding, right? Yeah. And I was working on a large-scale C++ application. In C++, you may know this, right? You don't have a file. You have a header and a CPP file. For everything you do, you have two files, not one, because they believe in giving you twice the pain, not just once. So now imagine this. You had to make a change to a certain function. How do you do that? You do a grep, and you find every file that's affected. Now you have a list of files to change, and you got to open one file at a time, and you got to change that manually. If you think that was barbaric, it was. And if you told me, design something, I'm going to say, let me think 700 times before I design it, because the cost of change is very, very high. Today, you're sitting around using an IDE, and you're like, I don't like that function name. You gently right-click on it, type the new name, and before you could blink your eyes, all the thousands of files are changed. And it says, would you like fries with it? Imagine the cost of change is extremely minimum. So what we need to ask the question is, you don't want to avoid change. You want to ask the question, I don't want to create change that is expensive. And if a change is not expensive, then it's no big deal. So we have to evaluate that trade-off. And we got to ask the question, is this going to cost me more, or is it going to cost me less? Not cost nothing. Because to cost nothing, you're going to end up spending a lot more. So you're not really costing nothing in the long run. So that's a question we want to ask. So here we say return, and we use a pattern matching syntax on a vehicle. And I'm going to say, if it is a car, and if it's a case, it's a truck, or a default, it's something else. So I'm going to simply say processing car. You can say logic, right? So you can say logic goes here. So similarly, you could say processing truck, and you can put the logic in here, right? So processing truck. And this is going to be no clue, whatever that is. So essentially, in this case, what are we dealing with is the question, right? So let me quickly capture this. So this is going to be, let me make sure I'm in the right file. So I'm going to move this to the sample.java. Let's go back here. So essentially, let's see, pattern matching, blah, blah, blah. Let's see, type pattern expected, line number 13. Oh, yeah, of course. So this is a car, and that's a truck. So essentially, in this case, you are saying, I want to process a car, logic goes here. So essentially, what are we saying here? we still have an object-oriented hierarchy, right? That's fine. And the hierarchy is in a third party, not in our code. And you're saying, I want to bring in the processing for a car or a processing for a truck. Nothing says you shouldn't do the following. You could have said, for example, this could be elsewhere as well. And this could be handle, you could say process car, right? Nothing wrong with it. You can take a car and you can process it. This could be returning logic for car processing. There's nothing wrong with it. So you can come down here and you can simply say, hey, if it's a car, I'm not going to put 50 lines of code there. That's horrible. So I'm going to call process car and pass the car to it. Absolutely, you can do that. But the beauty of that is you are providing these dispatchers to these functions. And by providing the dispatchers to the function, you're keeping that clarity in here. But what you did was you flattened the hierarchy. And you're not dealing with a parallel hierarchy or a visitor pattern. And that is not to say you should never do visitor. That is not to say you should never build a parallel hierarchy. But ask the question, are you gaining or are you losing? That's the question you want to ask. And I'm a huge fan of having different tools to work with. And generally speaking, rather than letting my emotion drive it, I like to prototype my code. And when I prototype and I implement using OO in one place, I implement using data-driven in another place, and then I compare it and say, which one feels better? What are the pros and cons? I can start listing the pros and cons, and then select which one feels better. And here is the beauty. If I don't bring my emotions into it, if I like it today, I'll keep it. If I feel that's not the right thing to do, I can always refactor it. And the beauty is, it gives an opportunity for us to experience two different ways of coding, and then we can take one that has better merits than the other ones and keep the one that is going to give us a better result. So not to be tied to data-oriented programming, not to be tied to OOP, but I would say evaluate. So when you face a new problem next time, when you feel like you can use a visitor pattern, for example, give it a shot by prototyping two solutions. And bring your team together and say, hey, let's not focus on which we like, but let's focus on which one is easier to maintain, which one is easier to understand, which one is less bloated, which one is easier to work with. And based on that, let's pick a solution. So essentially, I see this as a nice design pattern in that we can use the data-oriented programming and leverage the power of pattern matching and reduce the complexity in the code and the bloat in the code as well. So to summarize what we talked about three different types of patterns. Those that can still be used in Java, but things that are easier to use right now thanks to having Lambda expressions and things like that. We talked about patterns where we can benefit from things we didn't ever do before, but we can do now because we have these concepts. And we have newer ideas that can help us to reduce the bloat in code as well, and we can benefit from them as patterns as well. Hope that was useful. Thank you so much for being here.
All systems are nominal. Initialize Genesis sequence.